figure you got at least.
Yeah.
Several, yes.
Yeah, I have a question. Do you have any preference on what you want?
Go ahead. Any of them we do.
Yeah, most of
Pick
them. Can we start with, let's do 455.
455, tell me
Yeah.
what it is.
Pull it up real quick.
Solution is there, but maybe some.
Okay, 55. So previously we found in the field at the center radius B of a toroid.
All right, let me draw the toroid. So here's the toroid. It looks like such. It's got a radius. Is this B? Doesn't matter.
Outer is C, inner is A, middle is B.
On B. So then we have outer radius C, inner radius A. All right. That means the radius here is equal to C minus A. And we have all these terms, right?
Yep.
I'm just going to say we have N terms. And we want the inductance. Where do we want?
Find the inductance. Yeah, and
Okay.
then do it again with a certain number of turns and an iron core, 99.8%.
All right, look, we're just going to find the inductance of this thing in a simple way. I'm going to build an equivalent magnetic circuit of this. Are you all with me on this, class? Now, please be attentive here. So for an equivalent magnetic circuit, you start with the actual equivalent voltage, which is called a magnetomotive force. That MMF is going to be equal to simply the number of turns times the current in each turn. Do you all follow me on that? It's just think of it like a voltage. Now we're going to get the equivalent reluctance of this thing. And it's just like resistance. So if we want the equivalent reluctance, and the equivalent reluctance, just like, this is a constant cross-section thing. Y'all agree with this? So if I cut that and just straightened it out, it would look like this. The total length of this thing would be 2 pi times the inner radius, or times b. That's the mean radius, they call it. Y'all follow me? And the cross-sectional area here, that is simply going to be pi times the radius squared, which is going to be c minus a squared. Don't worry about that value. You all with me?
What do you do right there? The 2 pi B.
Yeah,
I cut this up and I just bend it out straight. The perimeter of this thing is 2 pi L, or 2 pi times the radius, right?
Okay.
The mean radius is b. Does everybody follow me? Are you with me? Okay. So I just break it right here and then bend it straight. And I'm just trying to show you how I would think about this. That's A. That means the actual reluctance from here to here, the equivalent reluctance of this thing. Reluctance is just like resistance. It's proportional to length, inversely proportional to area, and inversely proportional to mu. Just like a resistance, right? So here, I say this equivalent reluctance is the length, which is 2 pi b, divided by the area, which is pi right here, and it's going to be c minus a squared, right? And it's divided by mu. Now, I don't care what mu is. It can be mu relative to mu naught, or mu naught if mu relative is 1. It doesn't matter. Do you all follow me? Next thing we have to do, I'm going to stop for a second. Everybody with me on this part before I take off?
C minus, what is the C minus a squared?
Yeah,
Is
sure.
it-
Actually,
would it be C
the
squared
radius
minus B
is
squared?
this divided by 2. My bad. You're right about that. This should be divided by 2. And here's why. Look, we know the diameter of this thing, right? Diameter would be c minus a, right?
Oh.
C is the outer radius, a is the inner, right? That's
Okay.
diameter by 2 would be the radius. Do you agree with this? And he's saying that this thing is circular in cross-section. So he might even give you the radius for that one. So this would be this divided by 2, actually squared.
Wait. So you're trying to find the area of the toroid, right?
Of the
It'd be-
cross-sectional area.
Yes, cross-sectional area.
Oh.
Cut it. Just cut this thing in half. It looks like this, right?
Okay, that makes sense. Okay.
This area right here, the area here is pi times radius squared. What's the radius? Well, it'd be pi, and the outer part was c minus inner part divided by 2 squared. So it's pi over 4 c minus a. But I'm just trying to show you the method. We'll get to these values in a second, but try to be a little neater about this. So this is pi. It's really over 4, and then it would be what? C minus A here squared. I hope you all follow.
And then mu, right?
And we're going to put the mu in 1 second. You're ahead of me. We're good.
Okay.
So then it's divided by mu, and mu is mu relative mu r. Or mu naught times mu r. Okay? Now we have that. Next thing we need is the amount of flux flowing. Magnetic flux is like current. So it's just going to be the MMF divided by the reluctance. Well, you can write it down, so it's going to be N times I over this reluctance. I'm going to leave it as just RL for now, okay? Now we're going to use the flux linkage method to get this. Remember before when I talked about mutual inductance, if I had a current causing a magnetic flux through a secondary loop, if I found the flux through that loop and divided by the current, that would be the mutual inductance, right? Do you all remember that? If you had more than one term, you'd have to multiply it by n. Do you all remember that? All right, now watch me on this. So this is the amount of flux flowing through every one of those turns. If you think about this, each one of these turns is going to have that magnetic flux flowing through it, right? But there are n turns, right? So the amount of flux linked to these turns would be n times that. So this is the symbol he uses for this. This is flux linkage. Alright? And that's simply the number of turns, because it is something that has the same flux through each turn times the flux. So that's the flux linkage. Now, and this is not the energy method, but it's the same. It'll end up with the same results. Now, and it's oftentimes a lot easier to do it this way. Dr. Gross loves this. How many of that Gross in here? Okay, well, you probably heard him say this. So that means the inductance, and this would be self-inductance, is going to be the flux linkage divided by the current causing. This will never be a function of current unless it's a nonlinear system, and it's not here. We don't deal with nonlinear systems in general in these undergraduate courses. So this is N times the magnetic flux divided by I. Now we simply take all those values. I is going to cancel. You all with me? I is going to cancel, and I come over here, and I just start replacing things. I have N times the flux. That's the flux divided by I, right? So here I have N times this, so it's going to be N squared. Then it's times I divided by I and the flux. I's cancel, and the actual, the reluctance itself is 2 pi b. Get out of your way. Then it's divided by, I'll take the rest of the upstairs on this one. So this is the 2 pi b, then I have pi over 4 mu, so then upstairs it's pi over 4 mu, and it's c minus a squared. Now, obviously you can see some cancellation with the pi's, right? And we can multiply top and bottom by 2, so we're going to end up getting n squared. Whenever you have a coil like that, self-inductance will always be proportional to n squared. It's times mu. Then it's times c minus a squared on top. It's divided by 2b on the bottom. And that would be the inductance in henries.
Wait, what the 4?
Multiply top and bottom by 2. You get 1/2. And I'm sorry.
Couldn't the 4 just go to the bottom and make it an 8?
Yeah, my bad.
Yeah, it's
You got me
8.
on this. All right, that's my mistake. Y'all follow me on this? Now, you can punch the number, see if it comes out and agrees with. Does he have this effectively or not?
I think so. Check.
Yeah.
I believe.
Yeah, pretty much. Yeah, it's a little different.
What does he have?
Mu n squared b squared minus a squared over 2b.
B squared
That's what I remember. That's what I wrote down. Is that what he did, guy?
I have right here. It says L equals mu n squared divided by 2b times b minus a squared.
Okay.
Quantity
Not
squared.
b squared minus a squared. B minus a squared.
Wait, what is it called?
It's right here.
The same thing
It's
you
right here
got,
for
but
one.
except an 8 is a 2.
Also, C became B somewhere.
What? No, what is B the mean radius in this one?
Yeah.
Let me look at this.
It says b is a lot larger than c minus a though. If that.
Oh, it did say that in the problems. Wait. Yeah, it did say B is much, much larger than C minus A.
Not a
But
problem.
I
It's
feel
still
like.
going to be that form.
Yeah.
All right, so what did he use here instead of C minus A? He has what?
B minus A, and instead of 8B, it's 2B.
Okay, so look, so B, if you think about this, A plus C over 2 is B, right? Okay, so that means if I wanted to do this, C would be equal, if I look at this, that's going to be 2B minus A, right?
Yes.
All right, if I put 2B minus A, I get simply, this is going to be the 2B squared, right?
Yeah.
Yeah, it's gonna
2B
be
squared is going to be 4B squared, right? I don't know
It's
how
gonna
it
be
has it, but
2B
I'm
minus
sorry.
2A.
If I take a look at this, I had C minus A here
Oh,
squared.
it is the same.
So if I look at this,
Yeah.
C is equal to, 2B minus A. 2B minus A, wait a second.
Yeah, it's the same thing because then you factor out a 2 squared, which is going to be 4 over 8,
You're
so
right.
then it's 2b.
You're going to get the same answer.
Would there be a reason to put it in this form versus his form?
Convenience.
I guess just getting rid of C.
Yeah, you do get rid of a c.
I don't care. I mean, you do it, it's going to give you the same number at the end of the day. You all with me, class?
Yes, sir.
All right, I prefer he gives the radius or diameter of that solenoid and then separately gives the mean radius of the actual toroid. Of the small. All right, now what else? What's the next one? You all understand that? Okay, it's always boiled down to this. All right, you're drawing an equivalent circuit, makes it much easier. Got one for me?
I do.
I just started going to ask a question before he asked. Do you think it's a lot easier to use a magnetic circuit instead of just trying to solve for the inductance normally?
Yeah, oh yeah, if you possibly can, yeah. I mean, you can't always, because if you just have a long wire and then a loop, the self-inductance, you gotta calculate the B field and integrate. But for these things, where the field is assumed constant over the inside, yeah. Get reluctance, then you got it.
Yeah, that was a lot easier than what I thought it was.
I don't know how they did
Okay,
it.
then for that matter, let's do 4.54, which is like that.
Hold on,
Mm-hmm.
let me erase this.
Yeah.
Oh, wait. Briefly, can you do part B of that?
What is part B?
Find. I don't really care about. It
What
gives
is
you
the
some numbers,
answer?
but it says around a 99.8% iron core. What would that change? Rather, that's all I need to know.
Mu relative
Oh, okay, true. What would mu relative be in that?
0.9099 or 98 times the actual mu relative of iron. Or he's probably got it. Does he have something in the back where he gives the iron core value? You can
Probably.
Get,
You
yeah,
have to-
don't worry
you have to
about it.
look
That's
it
a
up on
material
Google.
parameter. He's just,
Yeah, you gotta look it up. It's a value that's like
That's
a constant value.
But we'd get that on a
Yes,
composer test.
yeah.
So.
that's
Most of our quiz and tests isn't just that. 'Cause, I mean, once you get that, you can plug numbers.
Just put the value of mu in, that's it.
Okay then. Then 4.54.
All right, hold on. Let me erase this. This is, you know, these are things, once you see them, it's like, oh, this is trivial. But sometimes you don't see it. And Whitmer's book he doesn't always do it the easy way. I'm going to tell you that sometimes he does it the hard way for a reason. He has a lot of exercises in MATLAB. I don't give you exercises in MATLAB generally. You're going to get plenty of that later. In EMAG 2, I think you have to, but this is EMAG 1.
Why?
Because when you have to do a project, now, I don't make this, I don't set the rules here. ABIT is an accreditation agency, and they specify a certain amount of projects involved in the classes and stuff, and the department therefore requires, when I teach EMAG 2, that you give a project, and it's a MATLAB project. I mean, if you want to use Octave or Python, it's fine, but they usually specify MATLAB. Okay, just level. All right, what's this one?
454. It says, consider a long pair of straight parallel wires,
Oh, this is my kind of problem.
each of radius A.
Okay, we've got a radius A of these wires. Okay, hold on. So the radius on both is A.
And then it says, with their centers separated by a distance D.
All right, in other words, center to center is separated by D.
Yeah. And then it says, assuming that the D is greater than the A, like a lot much bigger.
All right, D
Then-
is much, much greater than A.
Yeah.
Okay.
And then find the inductance per unit length for this pair of wires.
All right, well, if it's inductance, then the current has to be going this way. So what he's talking about is think of an extension cord.
Wait, why does the current have to be going that way?
Because if it wasn't going that way, the actual things would be repulsive. He's talking about a differential mode. You got current going this way, and then current coming this way. It's like an extension cord works that way. Think about it.
I'm sorry, that makes sense.
This is standard. When you're calculating the inductance of a wire, there's two things to worry about. There's the internal inductance of each wire per meter. Then there's how much inductance is in here. I'm going to show you a trick to do this. I'll wait for everybody to think about this. Now remember, we could do it with energy. Energy is a pain in the butt with this one. We go nuts. Dual flux.
Yeah, I think he does energy for this one.
He does.
So, I want to show you
He does
this.
energy.
Now, if we look at a per meter, you better do it per meter.
He does per meter.
All right, we're going to take 1 meter here. This is the length, and we want the inductance in that. Well, we've got the inductance of the wire, don't we? The internal inductance we calculate. Do you remember that? Right? So if he wants the internal inductance of the wire, this wire to here, we know per meter a wire, and this is going to be internal inductance of a wire is mu over 8 pi times the length. Well, we're taking 1 meter, so it's going to be that in one and that in the other. You all follow me? We're just doing 1 meter. This is the internal inductance here per meter. You're taking 1 meter, internal inductance here per meter is twice that, right? So it means the internal inductance total for this one is twice that, or it's just mu over 4 pi. And that's for the wire, whatever it is. This is just for the wire inside. Wires, I should say. Okay. Now the next thing we're going to do is find the amount of flux, magnetic flux, that's going to be in this region right here. Y'all with me? I want you to listen to me now, carefully. This is important that you hear me and see this. And this will help you on exams and in the real world. Okay? Now, if you think about this, the flux from this wire, the B field from that wire is into the board, right? Y'all with me? And
From the left wire?
going up, yeah. You with me? Now just watch. That flux is going in the board. When we integrate B dot ds, we're going to get a value. That would be the value caused by this wire's flux. Y'all with me? Now go the other way. This wire's flux into the board too.
Oh, so just be
Same magnitude, right? When we do the integration, we're going to get the same value for either wire when we calculate the flux through that. So we only do it once and multiply by 2. Does this make sense to everybody? All right. So we're going to say the total magnetic flux going through there. It's going to be a double integral. All right. It's going to go, and let me get to this in a second. Now, what is the magnetic flux? We're just going to take one of them. So I'm going to start here. Call that Z equals 0 here. All right, first I got to get the actual B field caused by this wire at a distance rho. Now I'm going to use rho coming from there, put this wire on the origin. Do you understand the reasoning behind this, everybody? You good with this, Chase? I'm going to find the B field from this wire. Well, this B field will be equal to mu Now times the H field, which is going to be I here, over 2 pi rho. Do you all follow me? It would be I over 2 pi rho if it was the H field. We multiply by mu and we get the B field. Do you agree with this, everyone?
Yes.
It would be into the board. It doesn't matter. You can call it A phi if you want. Now we got to multiply that by a differential surface and then do the integration twice. So I put a 2 out here. So the B field itself is mu I, mu 0 if it's there, over 2 pi rho. In the A phi direction, the differential surface is what? Think about this. We're going to stay in cylindrical coordinates. What's this differential surface going to be? Well,
d rho
it'll be
dz.
d rho, right? Times dz in the A phi direction. Right? Rho would be going outward. You can do with x and y, it's easy. Z's upwards in the A phi direction, so the plane of the board. So we get d rho dz. Now dz I put as the outer one. It's over 1 meter. We're calculating the amount of flux per meter because we want inductance per meter. So dz goes from 0 to 1. What about rho?
It'd be from.
A, right? It starts at A. We got the internal inductance.
Because this is outside the wire, so it's
Yes.
it's rho or whatever
A.
A to D minus A. No,
D minus 2A, right? Is it? Let's
No,
say-
it'd be
no,
D minus
A.
A. D minus A.
You're right, D minus A. Okay, so what does this become? Magnetic flux total is going to be equal to, well, I have 2 times divided by 2, so it's just mu 0 I over pi. See, the 2's cancel. A phi dot A phi is 1. A phi dot A phi is 1. Now the dz integral is just going to be 1. When I integrate 1 over rho, I get natural log of rho, right? And rho goes from B minus A over A. So that's the magnetic flux that's going through. Now we calculate the inductance. This is external, not internal inductance. And it's going to be that divided by the current causing. So the inductance, and I'll pull it external here, is just going to be this, divided by the current causing. And this is going to be, just going to really current. Mu 0 over pi times natural log of D minus A over A. If D is much, much larger than A, you can just say D over A if you want. You all agree with this, everyone? Mm-hmm. All right, now the total inductance would be that, whatever it is, and it's this plus this. Can you tell me if that's right?
That looks right.
Looks right. I think it is right.
I wrote that down somewhere.
Can you all follow me in the way to do this? This is a classic problem, by the way.
It is right.
These are classic problems. In other words, you might have got that in physics if you had, depending on the type of teacher, if you had advanced physics, probably, what do they call it, honors physics, you probably had that problem.
So the total would be this plus that.
Mm-hmm.
Okay,
Per meter.
cool. Per meter, yeah.
Has to be
That's what-
internal plus external. Now, one thing I'm going to tell you, this formula for induct, this is going to be, generally speaking, much, much larger than that. That's mu, or it would be mu 0 over 8 pi. Just look at this. Mu over pi is 8 times that right there, right? Now, the logarithm, depending on the separation, you might get 10, 20, so it's dominant. That's dominant usually, not always, but usually. Okay. Inductance per meter for 2 wire pair. What else?
What would it be if instead of doing the integral from A to D minus A, what would it be if you did 0 to D?
Infinite. Think about it. If you divide anything by 0, you get infinity, right?
Mm-hmm.
That's why you can't go there. If you had anything, then the inner radius is going to be right here. Anything by 0, it's infinite. The log of 1 over 0 is infinity. The log of infinity is infinity. Follow me?
Yes, sir.
That's why you can't go that route.
Why does it, so do you define the origin like 0 at like in the middle of that wire, or?
You need some reference. So right down the wire makes perfect sense, right? Everything's symmetric about that. That's the reason.
Okay, so you just define that as 0 because that makes it
And
easier.
this is good. Yeah, always make your life easy. It's tough enough without making it and without adding more complexity.
So then you only need you need the distance between the centers basically.
Mhm.
Okay.
You need to know where this thing is relative to this thing. That's what it comes down to. It doesn't matter if it's center to center or it's outer radius to outer radius. You have to have some way of knowing what the spacing is so you can do the integration correctly. Okay. He shows something weird in that book, but I'm looking at it. Anyway, I hope you understand. Do y'all understand this?
That makes sense, yes.
All right, what's the next one? I'm glad you guys are asking questions.
I got 459 as well.
Give me 1 second. There's all sorts of weird problems you can come up with. There's a class, there's a couple of books. One of them is called Hate, H-A-Y-T. If you look online, you want problems, like tons of problems, there's solutions for it too. Look at the earlier editions of Hate. I had that text when I went through my undergraduate career in electromagnetics and EMAG 1 and 2. And I'll tell you, it actually does a fantastic job. Some of the problems he comes up with are they're brilliant, but they really, they test the students' real understanding. Go ahead.
So 459, it says a 4 centimeter diameter solid nickel wire.
Hold on. Oh, this one. So we got a diameter of 4 centimeters.
Mm-hmm.
All right.
So it's centered on the z-axis, conducts a current with a density J equals 4 rho in the AZ direction.
Right. So this is on the z-axis. Assume z is coming out of the board. I hope you can imagine that. Class, you with me on this?
Mm-hmm.
I'm just taking the cross section. Z is coming out of the board, and then you say it's equal to what?
4 rho in the AZ direction.
AZ amps per meter squared. I
Yeah.
hope.
Well, it's per centimeter squared.
Can we just pretend it's amps per meter?
Huh?
Can we just pretend it's amps per meter squared?
What does he want out of this?
He wants to find the internal inductance per unit length for the wire
Well,
with this current distribution.
we're gonna do something. We're gonna do meter squared and make this meter squared. What's the diameter of 4 centimeters? It's now 4 meters. Brilliant. I think it's gonna work, guys. I think it's. What does he want now? The inductance, internal inductance.
He wants internal inductance per unit length of wire.
Okay, guys. This one's gonna take a little bit more. Here's the deal. You got a wire. It's infinitely long, and we got the current density. So what we need is the magnetic field. With me?
Yeah.
So we're going to use our faithful friend, Ampere's law. And we're going to say it's cylindrically symmetric. Do you all agree with that?
Yes.
I hope.
I would hope so.
Okay. Here I'm going to come out of radius rho, and I'm going to go ahead and make my Amperian loop. Right? And I know that the integral of H dot dl over the closed loop is equal to the current enclosed, which would be a double integral of J dot ds. Do y'all agree with me? I'm just putting it down. I'm going to put the values in a second. You with me, class? Chase, you good with this? All right. So what is this always? If it's a cylindrically symmetric thing, what is this?
H times 2 pi.
2 pi rho.
Yeah,
Right, so that the H field is going to be H of phi of rho times, and this is going to be times 2 pi rho, right? Matter of fact, let me get rid of that function of rho. It's implicit as a function of rho. So we're going to do it this way, and that's equal to this. Well, what's this going to be? Well, technically, it's a double integral. J is given. My J is going to be 4 rho AZ, right? That's amps per meter squared times the differential surface would be rho d phi d rho in the AZ direction. Now I just put down the differential surface is right here. This is simply J. Agreed, class?
Yep.
With me? Now, next I got to put the limits. All right, so where does phi go from?
0 to 2 pi.
Right. got me.
And the other one's from 0 to rho.
And this, and here I'm going to be careful. 0 to rho, I got to prime these because technically the limits can't be part of the kernel of integration. That's the only reason I'm doing it. You're with me, class? All right, what happens? AZ cancels, right? Now I have this thing equal to, let me do it up here. So I have HV equal to 1 over 2 pi rho times the integral of this. Well, this is going to be 2 pi, right? And then look, I have rho here, prime, or rho prime. So it's going to be squared. The integral of rho squared d rho is rho cubed over 3 from 0 rho will be rho cubed over 3. You agree with that?
You dropped a 4.
Yeah, that's
Yeah. Times.
But besides that, I agree with that, yeah.
Huh?
Yes, that's good.
I'm going to get rid of the 2 pi if you don't mind. All right, so I'm going to get rid of the 2 pi. And you can see rho into rho is going to be rho squared up top. So now I have my rows, I have h. To get b, I multiply it by mu. Do you agree with this?
Mm-hmm.
We can do it a couple different ways. I think I'm going to do it this way to be clear to everybody. So now we get the energy density. And I don't know if you did it this way, but I'm going to do it this way. All right, what's the magnetic energy density? Well, it's 1/2 h dot v is one way, or it's 1/2 mu magnitude of h squared is another way, or 1/2 magnitude of v squared over mu is another way. I'm going to do it this way. They're all the same. Do you agree with this, class? Can you see it? All right. So what happens over here? The energy density becomes 1 over 2 mu, or sorry, 1 over 2, times mu, or 1/2 mu, and then I have to take h and square it. So that means I'm going to get 4 squared, well now, let me do it this way. I better take 4/3 squared, and then I get rho to the 4th power here, and that's going to be in joules per meter cubed. Does everybody agree with that? Take a moment, make sure you do. Agree?
Yes.
Okay, are you with me? That's the energy density, right? Now, where we're going with this is we're going to say that the energy density integrated, or 1/2 L, and this is going to be self-inductance, so I just call it L, times I squared. Now this is going to be inductance per meter, right? Are you with me on this, class? 1/2 Li squared is the energy in an inductor. We need the energy in an inductor of 1 meter long, and that's equal to the integral of the energy density over the volume. Now I'll put down the limits in a second. Does everybody follow me on this one? I don't know how he did it in the book. I'm doing it this way.
Oh, so it's the triple integral of Wm?
Yeah, remember, that's magnetic energy density, joules per meter cubed. We want the energy in joules, so we got to integrate over the volume it exists in.
Yeah.
That's a density. With me, class?
Yes.
Yeah.
All right. So, what happens? Well, 1/2 Li squared is equal to, it's a triple integral. Let me put the current density, the energy density first. So this is 1/2 mu 4 over 3 squared. I'm going to take all that out in front, actually. So that's 1/2 times 4/3 squared, right? And that's times rho to the 4th. Now I'm going to go inside. Now I'm going to have this triple integral here. And I'm going to have rho to the 4th. Y'all agree with this? I'll take all the constants out in front. And the mu actually comes out in front too. Y'all agree?
Yes.
Just take a second. Y'all with me, class?
Yeah.
Now, after that, now I'm going to multiply this by the differential volume. We're in cylindrical coordinates, differential volume is rho d phi dz, and it's times d rho. And the order is unimportant. Okay? Phi goes from where to where, guys?
0 to 2 pi.
That's right. So this goes 0 to 2 pi. Z goes from
It'd be 0 to h.
0 to 1.
0 to.
8
it
times
doesn't
per
matter.
meter, make it 1.
Well, it doesn't matter because you can
Yeah, I mean, it's going to cancel, yeah.
Is it acceptable if I integrate from 0 to L and then my final answer will be L divided, or inductance divided by length equals
Yeah, but
think
why
it's the
not
same-
make it
that's the
1
same
since it's
thing.
inductance per meter?
I think it's the same thing. You can
L,
just-
yeah, I
just
mean,
say
you could
one
do it
to
that
the-
way.
yeah, but that's acceptable if I want to.
Absolutely.
Yeah, that's all.
All right, and finally, I integrate rho from where to where? 0 to the radius of the wire, right? We need the total energy per meter, right? Huh?
Okay, that makes sense.
Only internal, right? He only wants internal inductance.
Okay, let's see.
Guaranteed, because the external inductance is going to be infinite. All right?
This is internal.
All right, so what happens here? Just look over here, you're going to see something. Wait a second. I forgot the I. Yeah, we haven't got I yet. I got to get I. Now, so how do I calculate I? All right, maybe I'll stop for 1 second. You all see the 1/2s cancel?
Yes.
All right.
Yes.
Now, I need I so I can divide by I squared. With me?
Yes.
What is I?
Integral. It's integral of j dot ds.
Which is
Gonna be the
J
same
is
integral.
4 rho, right?
Yep.
And what is it? 4 rho?
Yeah, it is.
4 rho. Is it?
And second row comes out of a ds.
4 row.
Oh, sorry. 4 rho times what? Just 4
Times-
rho AZ?
Yes.
AZ. All right, that's fine. And it's dotted with the differential surface, which is rho d phi d rho AZ, correct?
Yes.
Rho goes, or phi goes from 0 to 2 pi, correct? And rho goes from 0 to A. Now that's I. So what's I going to be? I can take the 4 out in front. AZ is 1. D phi from 0 to 2 pi is 2 pi. And then when I integrate, what do I have? Rho squared, d rho is rho cubed over 3. From 0 to A is A cubed over 3. So that's I. Agreed? So, what did I do? All right, so here's what we're going to do. We're going to go ahead and find L by finding that, and then we're going to divide it by I squared. Everybody with me? I'm going to do it in this book, but I need your help. By the way, does everybody follow the thought process, the logic of this one? All right, so the next thing we're going to do is evaluate this integration. Now, just work with me here. I'm going to take Li squared here. I'll just leave it aside. Over here, when I do the integration, phi from 0 to 2 pi is just 2 pi. And I better take the mu over 4/3 squared out front. And then, from 0 to 2 pi, I get 2 pi. Now, when I integrate dz from 0 to 1, I get 1, right? And then when I integrate, what is this going to be? This is going to be rho to the 5th, d rho is rho to the 6th, right? Over 6. Or a to the 6th, right? Over 6, because we're going to evaluate it from 0 to 8, correct? Now, it's equal to this, so therefore L per meter is going to be all this. I'm going to write it down and see what happens. Mu over 4/3 squared times 2 pi here times a to the 6 over 6, and then I can divide it by the current, and it's the current squared, right? So it's that squared. So now I have 4, what is that? It's really 4 times 2 pi over 3. Okay, let's do this. All right. That's 2 pi, so this is going to be 8 pi over 3 a cubed. 8 pi over 3 a cubed. And then I got to square it, right?
Yep.
All right. Now, I'm gonna just suggest, take one look at this with me, and I gotta make some comments. Do you all follow me on this one? This is one of those problems that's more irritating. You gotta be very focused and a good bookkeeper. But it's not a hard problem to understand conception. From the current, you get H. From H, you get B, or get the energy density. From the energy density, integrate over the volume. You get the total energy, set it equal 1/2 Li squared. And then equate the two, and you get L. That's the method. Now, you can see I'm going to get A cubed down here, right?
Yep.
Let me just do this. I'm going to get rid of that, because I got A cubed squared is 8 to the 6. 8 to the 6 goes away, correct? What else happens? The mu is out in front. How much cancellation do we have?
4/3 canceled, and one of the 2 pi. The 2 pi in the numerator cancels, leaving just a 2 pi on the denominator.
A 2 pi?
Yeah. It'll be mu.
It's a pi squared.
Mu over 6 over 2 pi, or mu over 12 pi.
Yeah, that looks right. Is that the answer?
I think that's right, guys.
Look at this. Is that it? All right, we turned everything into meters because I hate centimeters.
He has H because he didn't do 1 meter, but yeah.
You what?
He integrated from 0 to H, so yeah. But
Like
he has,
you did.
Yeah.
All right, class, you good with that?
Yep.
These problems are a little tedious. You get irritated with these integrations sometimes, but they're not that bad. Just methodically go through them and keep the books on these things, because you can get some really screwy answers if you don't. What's the next one?
4.61.
6. You missed it.
Actually, let's do 4.6. Yeah.
Anyone?
All of them section 6. Those
We can
are,
do
They're
it.
pretty much all the same. Let's do 4.6.
Let's start with 4.60.
Yep.
all
4.60.
those,
Sorry.
all the new stuff.
4.60. Let me erase this. It's not supposed to rain, is it?
Check.
I have this. Not really bad concern, but
It's supposed to rain it's got a 40% chance from 6 to 8 tonight. Other than that, no.
I have a meeting to.
just make sure you get the, look at the video towards the end.
Yes, sir.
And then I'm going to assign some homework, and the quiz is going to be on this stuff. And the quiz is on everything we're talking about.
Just inductance and magnetic circuits.
Yeah, and anything else that no, that's it. You can predict what I'm going to do. It's not, I'm not going to go back in time. All right, hold on, I'm going to sneeze.
We're doing 4.6 or 4.6.
Go ahead.
4.6.
Pardon me.
Bless you.
Thank you. 4.67. Hold on for 1 second.
Oh, actually, my 4.6 might be better. Because it seems worse.
What's that?
Because it's harder.
Yeah.
How about, well, I mean, you pick.
We'll do 6.1. It's harder.
Okay,
We
hard.
can do both of them.
All right, let's go with 6.1.
They're the
What does it
same.
say?
Okay. 2 centimeter diameter toroid.
Okay, so we got this. And this is what now? Is this the 2 centimeters?
No, okay. The toroid has a 1 meter mean radius, so
Okay,
it'd be
this is B is 1 meter.
Yeah.
Okay,
and
1 meter.
The thickness would be 2 centimeters.
Oh, it's 2 centimeters thick, or diameter or radius?
Diameter.
Okay, so that means the B here is 2 centimeters, and that means the radius R from here to here, R is equal to 1 centimeter. Go ahead.
Oh wait, what? Wait.
Hey, what?
Oh, here it is. Okay, so we have a graph.
Oh, yeah, all right. Here's why. We got to extrapolate the value of, this teeter-totter crap. Yeah, what they're doing is, they've got B versus H graph. This is very common, by the way. He's just showing you, he's getting you exposed to it.
So this is graphing mu.
Here's what he's going to have here, basically. Look, he has B on this axis and mu on this axis. They'll do something like this. But I'm going to make a comment here. I mean, not mu, H. Sorry. He's going to have B versus H. This will be H here. Now, I want to just mention this to you. So B is equal to mu H, right? this is a cool problem in a sense, but it's exposing you to something. I want you to hear me on this one. It's important in the general sense that you understand this. If you don't, you're going to look like an idiot on the job if they do anything with magnetic, any kind of high, anything with a lot of current and you have iron cores. It's important to pay attention. So listen. For this one, as H gets bigger and bigger, this will asymptotically approach a slope of mu 0, all right? Down here, it'll have a larger value. Mu relative may be 50, 100, but as, it's called the magnetic alignment, all of these little things that are magnetic, called magnetic moments, but they're dipoles. When everything gets aligned, it becomes saturated. You can't get any more magnetic energy into that more than mu 0. Remember, magnetic energy is 1/2, and it's B dot H, or 1/2 mu relative mu naught times H squared. Now that mu relative at the low end has got a large value. But as you start getting larger and larger value of H, all of a sudden it gets saturated. You can't align anything after that. And now the increase in energy just has to do with this, mu 0. I'm just trying to explain it in a way that it's not. So now he asks us to estimate the value of inductance. Is that it? For
Magnetic field.
All right. Now for this right here.
That's not. So we have mu R1. Mu R of the toroid is 10,000.
Well, wait. Yeah, but is this the graph of it?
Yeah.
Well, it's where's mu R 10,000, down here or up there?
It's a core wrapped in another
Yeah, there's a thing wrapped around the core too. But
material.
All right. Now, getting back to the fun problem. This is 6-1, you said?
yes, sir. Page 284.
Figure 4.59. A 2 centimeter diameter toroidal core with mu relative is wrapped with a 1 centimeter thick material. Wait a second, this isn't referencing that graph. Sorry. All right, we'll do it.
I referenced the wrong figure. That is my bad.
This is not bad at all. It really is. So here's what we got. Let me just tell you, I'm going to redraw this.
Yeah.
Y'all some goo.
Whoops. But for that matter, I'm going to do 4.6 as 2 as well.
Let's try this one for starters.
Just to go off.
Then
Yeah, I know.
you'll see. It's just iterating. You've done these things where you have to iterate. You can use Newton-Raphson's or any kind of thing like that. Okay, so for this one, we got big one, like so. Then inside this, we got another thing like this. We got an inner, if I can only do it like easy. Let me try this one. So I'm trying to show you something where there's going to be I'm going to give you the cross section. You got something in the inside here that has a given radius. And then you got a bigger one. So if you take a look at the cross section of this thing, now bear with me. Does he say, or let me do it this way. So you got an inner radius, and did he give you diameter or what? D1? What's the inner radius? It's got the mu relative 10,000.
It says in figure, blah, 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 a 2 centimeter diameter toroidal core
Right.
with blah, blah, is wrapped with a 1 centimeter layer on top of it.
All right, now you got a layer over here, so that means this thing has a total distance. If you want to call up the diameter from here, this diameter is going to be equal to 4 centimeters, right?
Yes.
Because it's twice, right? Now, I'm going to tell you, he gives you a mu relative of the inner one, and it's equal to 10,000, right? What's the outer one equal to?
It's equal to 3,000.
All right, so mu relative 2 is 3,000, right? Now, you guys are smart. I'll give you that. When you look at this for a second, this looks like we got two parallel reluctances, if you can look carefully. Do you all agree with that?
Wait, parallel.
Yeah, because it's the stack on something.
Yeah.
They're side by side, the flux is penetrating this way, right?
Yeah.
Let me show you what you're really looking at. You're going to have a magnetic circuit plus the minus. Here it's going to be the number of turns times the current. He has to give you something like that.
Yeah, we have both turns and current.
All right, now after that you got the first reluctance. I'll call it reluctance 1 from the inner core, and parallel to that is going to be reluctance 2. All right, now I hope you can see this, right? Just if you want, just cut this in half, because he's going to have something like, what's the radius of this thing B? Is it 1 meter?
Yeah.
All right, and he's going to say that B is much greater than the diameter or radius of the two other ones. You all agree with that? Now, if you cut that right there, just cut it right here and straighten it out, now you got something like this, right? Here, the length L is just 2 pi B. You with me? Now here, it's basically you got two reluctances in parallel. You got one, the inner one, and then the outer one. Do you all follow me?
Mm-hmm.
So the inner reluctance, R1, reluctance, remember, is going to be equal to the length over, and then it's going to be cross-sectional area divided by mu. Okay, the length of this one, by the way, we might as well make them the same, because assuming B, basically the radius is not going to be a big factor with length. Y'all follow me in this class? Because basically this thing's got a 1 meter and we're talking about centimeters. Right? So here it's going to be 2 pi times 1 meter. You said the diameter or radius is 1 meter?
Yep.
All right, divided by the area of the inner one. Well, the area of the inner one is just pi a squared, right? And A is 1 centimeter, or 10 to the minus 2. And then mu of this one is going to be mu naught times 10,000. Now there's 10 to the 4. And that would be the reluctance of the first one. Do y'all agree with this?
Yes. Yes.
What about the second one? Come on. Well, this is the same, the length, right? It's going to be 2 pi. I'm assuming that the radius of this thing is small compared to the mean radius B. All right?
Required, yes.
All right. So that's the length, 2 pi. What's the area? Pi. And now we got to take what? Outer radius minus inner radius squared, right? So it's the outer radius, which is going to be 2, minus inner radius is 1, and we got to square. Do you agree with that?
So it's 2 centimeter, wait. 2
B
centimeters
squared minus A squared. It's going to be, the outer radius is B, right?
Mm-hmm.
Or it's 2, right?
Yes.
And it's got to be squared. Minus the inner radius squared, right?
Yes.
All right, so it's going to be B squared is 2 centimeters. I'm just going to put B in there. Then I'll put the thing. So it's going to be 2 times 10 to the minus 2 squared minus 10 to the minus 1 squared, or minus 2, pardon me, squared. And that's going to be reluctance 2. Now you all see they're in parallel, right?
Yes.
If you got inductors in parallel, you can do it 2 ways. You can calculate the flux here, right? Just take this divided by R1, and you can calculate the flux in the second one, this divided by R2, and add the fluxes, and that's the total flux. Then divide, that would be the flux flowing through there, then multiply the number of by the number of turns, you get the flux linkage, then divide it by the current, and you could get the inductance. You with me?
But it asks for the B field.
Where?
It just says find the B field, the magnetic field intensity in each
You're
material.
not reading the same problem.
It's not a problem.
461
Is it 6-0?
says.
Oh, then I'm wrong.
461 says.
How much magnetic flux? You're correct. I read the
It
wrong
says
problem.
magnetic field intensity, same thing, of each material.
That's no problem. Now look,
Yeah.
I want to show you this. Do y'all agree? Just hear me. If I want the magnetic field intensity in the inner core, if I find the total flux in the inner core and divide it by the area of the inner core, I would get the B field, right?
Yes.
Right? So how much flux is in there? This is like a voltage. It would be Ni divided by reluctance 1. Do you agree with that? So the flux flowing through 1, magnetic flux 1, is going to be Ni divided by reluctance 1. That's reluctance 1. The pi's cancel, so I'm going to divide by 2 over mu 0 times 10 to the 4th. And that's it. Now this, I'll get out of the way, is the flux in Webers flowing through that first one. Do you agree with me?
Yes.
Then if we divide that by the area, then we get the B field in region 1. Now, what's the area of the first one? Well, it's pi, right? Wait, wait a second. Did I do that here?
I think your 10 to the 4th might cancel with
Hold
the
on,
centimeters.
I forgot the 8 to the 4th. Hold on. Let me rewrite this thing so I get everything right. So it's the flux Ni, I'll get out of your way, divided by, you gotta put the whole flux down here. Flux is Ni divided by that reluctance. It's 2 pi over pi. And here it's a squared, that's 1 centimeter squared times mu 0 times 10 to the 4th, which is the reluctance. That's the flux flowing through there, and I have to divide it by the area, which is divided by pi a squared. Okay,
Wait. Why? Wouldn't it be mu relative? Because mu relative.
That's
is-
10 to the
oh,
4th.
that's how you got that. Yeah,
I can put mu relative in there if you want, but y'all with me on this?
Where'd you get that pi a squared?
It's the cross-sectional area of the inner one right here. Think about this. Here, this is the area I'm talking about, right? Diameter is 2, so radius is 1. 1 centimeter,
Okay,
right?
so it's basically the. Oh, so you're saying that. Oh, I see what you're doing. You're saying that the Ni over the reluctance equals that fancy squiggly thing over the A, and
But
the
you're
H
going to
is
see
there.
one thing here. Just look carefully.
Gotcha.
What do you see about the pi a squared?
It's gonna cancel.
Cancel.
Right. So I get this. Now, you can mess with this, but it should be Ni over, or times mu 0 times 10 to the 4th, or mu relative. I'll just put mu relative for you. Over 2 pi. Does he have something?
Wait. The pi's canceled. On the left.
Pi.
Wait. No, that's the reluctance. Never mind.
This should have a 2 pi, right? Does he have that answer?
Yeah. I don't know. I don't know if he has that answer. I don't know if the answer is.
Who has the
Well,
answer?
I'm trying to make sure I get this right.
You with me on that?
This is whack.
It's pi. Wait, so it's the pi. Sorry, I'm just trying to get this in my head. All right, I got what you got.
This is definitely the weirdest topic in my opinion so far.
You get it, it's trivial. Think of the analog between circuits and magnetic circuits. That's all you do.
He gets, so this is for, he wants the H field, but that's the B. So he says B equals,
You want the H field?
he just multiplies
Just
by
divide
mu.
this by that, so it's Ni over 2 pi.
Yeah, it should be. Yeah, I think that's right.
What does he have?
I don't know. He doesn't have. He just has numbers.
Oh, well, put in the numbers, but it's going to be
62.
that.
Ni, because N.
Oh, he has Vn as n times I.
That's right.
Reference to the bottom.
You got Vn over the reluctant. Yeah, I think what you got is right.
It is right. Did you follow me on this class?
It is right.
It can look funny, but that's it. Essentially, you're building what? An equivalent electric circuit for the magnetic circuit. The reluctance is the thing that's stopping the flux or stopping the current and the resistance, right? The force driving it is N times I. Right?
Is there anything in a magnetic circuit that behaves like an inductor or capacitor in an electric
Now
circuit?
you're going way off the topic. Now you're talking about magnetic energy. Yeah.
But there is.
Well, sure.
Okay.
What is the thing about this? When you have an inductor in electric circuits, 1/2 Li squared. In a magnetic circuit, you don't have, I mean, if you think about this, what you really want to do is use a magnetic circuit to calculate inductance. So there's no equivalent like fictitious magnetic energy. It's real energy. It's 1/2 mu h squared. Don't worry, he's going somewhere with this. That's a little. The analog or the analogy drops after that. All right, we just need B field nature.
Okay.
Now what?
So would you do the same thing, that same process? See, it's BM1, you do that for this for
Oh
R2
yeah.
as well.
To get the second one, what do you do?
Just the exact same
All right,
thing.
just Ni divided by that reluctance. That's what? The flux,
That's
right?
the flux over the
Flux
area.
divided by the cross-sectional area would be the B field divided by mu.
And then the areas cancel again.
Yeah, well, I think so. Yeah, they do.
And everything works out.
Yeah, life is good.
Life is good.
Maybe. What else do you got? I figure you got a few more.
Yeah.
You're good.
Okay, now we can do that graph one if I pick the right problem this time.
Take that graph. No, I don't hate
Which
it.
one?
It's not
462?
gonna- I can't extrapolate, but we can estimate.
Either 60 or 62.
What is this one?
Either was.
What?
Let me put it up in one second. Oh yeah.
This entire class has been questions.
Nobody asked me anything about the force of electrons flying around.
No, the force, those were really easy.
Oh, those were all, yeah, they were, as you say, trivial.
I thought so.
Those were stupid easy.
Yeah. These are not stupid easy.
I got that instantly. Maybe I'm the only one.
Yeah, no.
I thought they were
very,
It was just cross
They're
products.
like, they're honestly high school physics.
yeah.
Yeah, they're pretty easy.
They're not. All right, go ahead.
This is not high school physics.
All right, this is the crazy one, right? Graph.
Okay, so we have a 2 centimeter diameter core of a toroid.
I hope, hold on. Let me just draw this. So we got this 2 centimeter diameter. Wait, this diameter or the mean radius?
Not mean radius. That diameter, the diameter of the toroid of the
This?
that's the diameter of the cross section.
All right, so A is 2 centimeters.
Yep.
Okay.
Mean radius is 60 centimeters.
All right, so that's this 60.
Yep.
All right, B is much greater than A. Go ahead.
We have 10 amps of current
Oh my goodness, I love 10 amps.
and 100 loops of wire.
10 amps and equals 100. All right.
And it's a 1 millimeter gap in the bottom.
Huh?
There's a 1 millimeter gap in the bottom from the
Oh, that rat.
Wait, where's the 1 millimeter gap?
current page 272.
Okay. And
That's it.
All right, that's okay. That's not a problem. So you got a 1 millimeter gap.
oh, I see it. Wow, that's disgusting.
It
No,
says
it's
find
actually
the
not bad at
magnetic
all.
field intensity in the
So
1 millimeter
B gap is 1 millimeter.
Yeah,
They want what?
Magnetic field intensity in there.
This is trivia. All right, don't panic. I'll show you. What's the bar made up, by the way?
It's just characterized by the graph.
All right, help me out here. So, if you look at this is H versus B, right? Oh, God, I wish I have to estimate the slope of that line. So, you guys got eyes. What's that slope down here?
The slope right here.
At the beginning.
Good
Rise over run. Just take a
Good
straight
question.
line. You need that. It does this kind of thing. Look, it does this. Comes right. It's basically a straight line here. So find the
Like
slope.
0.002.
Rise over run. What is the rise? Just find a point like from 0 to where it's 10 or something. What's the run?
It's about 0.4 rise, 200 run.
So H is 200.
Yep.
200 amps per meter, and the
B is
vertical is
about 0.4 teslas.
0.4. Now, B is equal to mu H, right?
Yep.
That means mu down here, the low end, is approximately equal to B over H. I mean, if I take a look at this, so I should say, delta B over mu, and this is approximately at the low end, is equal to delta H, or mu at the low end down here at the origin should be approximately equal to delta B, and you said that was 0.4 over 200, right? So it's 2 times 10 to the plus 2, and this is 4 times 10 to the minus 1 over 2 times 10 to the 2. There's 2 times 10 to the minus 3.
Yep.
And that would be henries per meter about, right? Now that's down at the bottom. Up here, it's going to go to mu 0. But I'm going to just show you how to construct the problem. You with me, class?
Yes.
All right, now this is iterative. First, you all agree if I cut that bar, I can turn it into 2 series reluctances. One reluctance has to do with that little gap, and the other has to do with this. Are you with me?
So series reluctances would be, yeah, okay, got it.
You all with me on this, class? Just look. Here's this. I'm going to cut this, straighten it out. Now what do I have? I have this kind of deal. I have something with a length that's approximately equal to, the total length is going to be 2 pi times 60 centimeters. Well, this is about equal to 2 pi times 0.6 meters. You with me? And then you got this little gap here you have to deal with. So this gap itself is, what is it, 1 centimeter or 1 millimeter, right? The gap length is 1 millimeter. Now, I'm going to draw the equivalent reluctance model of this in series. You with me?
Okay, wait,
There is a reluctance here, call it of the bar or the toroid, and there's a reluctance here, the gap. Okay? We're going to do the reluctance of the gap first. It's easy. You with me?
yes.
Okay. I'm sorry. Hey, come on, I'm going to do this one.
Okay, I'm good.
So these are series, right? Because they're together.
Yeah. I mean, all the flux has to go through this bar and has to go through here. Here you go. Okay? So, this, the reluctance of the gap, well, I've always said it's L over mu area, right? They give you the length of the gap. It's small. It's 1 millimeter, right? It's much, much smaller than the radius. So, it's going to be 10. I'll just put L gap. It's L gap over the area, which is pi, and it's going to be times a squared, right? And what is the permeability of the gap? It's just there. It's 1 times mu 0, right? Mu 0 is 4 pi times 10 to the minus 6. I'm going to just put mu 0. So that's the actual reluctance of the gap. We'll put in some values in a second. You all agree with that? What's the reluctance of that bar? Total length, which is 2 pi times 0.6, that's total length. It's divided by the area of the bar, which is going to be pi a squared, right? And then it's divided by that permeability that we're going to have to iterate on this one. You all with me, class? We're going to start with the largest value of permeability, which is about 2 times 10 to the minus third. So then we go ahead and we put 2, now I'll tell you what, let's go ahead and put down mu relative, and I'll show you what I mean by this. Here, it's going to be mu relative. It's going to be a function of h times mu naught. Now, you all follow me? I'm just showing you what the formulas would have this. Okay?
Okay.
Now, what we know is the equivalent circuit would look like this. I would have, think of it this way, I have an MMF of n times I. He gave us that, right? Then we have 2 things in series. The first thing you're going to have is this reluctance, which is that we just got for the bar, and what happens? It's going to be 2 times, well, I'm going to put it down as, I'm just going to put reluctance of the bar here. and this is going to be reluctance of the gap here. Now we can find the magnetic flux here by saying it's equal to Ni over the sum of reluctance of bar plus reluctance of gap. Can you all follow the thought process? With me?
Yes.
Now, if that, here's the deal. That's the flux flowing, right? That flux is flowing where? All through here. It's the same here in the gap as it is here, right? What we need to do is find out what the H field is, or B field here, right? So what we're going to do is, if we know that's the flux flowing, well, what is the H field in the gap? First, the B field would be this divided by the area in the gap, right? I'm going to show you this. So I'm going to divide this by the area in the gap. Now that's the B field in the gap. But we want H, because H is on the horizontal. So we say if we take this, that's equal to mu times H, right? That would be the value of H in the bars. Here's how we go about this. I'm going to just tell you this is how it's done. You ready? I don't know how he does it in the book, but this is the way they do it. All right, now here's how you do it. You start by saying, let's assume that the bar has no reluctance at all. Everything's caused by the gap. And let's start by saying, what would this flux be right here if just the reluctance of the gap is there? Well, this would be equal, this is called the first permutation. It would be Ni. Then you would divide this by reluctance of the gap, which will not change. You're going to get a value for flux. Everybody follow the thought process?
Yes.
Then divide that by simply the area, and now you have the B field in the gap, right? Now, once you have this, you can get the H field, right?
Is that what we're looking for?
Now we're going to use this because we got to iterate. We got to go back over here to this plot and see where H is. Right? We got to add some more P. So now if we divide this by mu naught in this case, now we're going to get our H from the first iteration of H1. Are you with me? This will be divided by mu naught. So if you do, I don't know what it comes down to, but you follow me on this? If you look at his solutions, he's going to do something like this. He's going to iterate to the value. You're going to get this first value, okay? Okay. Now once you have that, you come over here. You say, that H field H field's like the E field. H field anywhere in that circular path will be the same. B field will change, but the H field intensity will be the same. So now I come over here, I get that H field, and I look and I see where in fact it is. You all hear me? Now once you figure out that H field, now you do the second iteration. You get the B field that would be in the main bar. You all follow me? We're going to extrapolate, find out where H is. I don't know where it is, by the way. It may be up here. Once we get that, now we get the B field would be there. Okay? You with me? We're just here's the deal. Right here, we can figure out what the mu is. That's the point, because it's just the slope of the line, right? Once we get the slope of the line, come back over here. And now we do this part. Second iteration, Ni is still the same, reluctance of the gap is still the same, but now we add the reluctance of the bar to this. And it's going to start increasing, and the total flux is going to decrease. But what you're doing is iterating. It's an iterative process. Do you have the solutions? He does. Let me take a look. I'm going to tell you that's exactly what he does. A good question is, would you ask us something like this on the test? No.
Yeah, I was about to say, if I see this in the final, I might have to just read it out.
I'm not going to ask him a question.
I might just give it back to you.
Yeah.
I'll see you next semester.
All right, he has from the chart, he's doing it, evaluate that, our total is that, then took the value B and repeat 4 or 5 times. He's an iterative solution. That's the only thing he does there. All right. Now, I'm going to say this. He has a bust.
It's not right. What time it was?
It's not hard. All right? It's iterative. And you've done iterative problems before, haven't you? Okay.
Yeah, you
guys.
just plug it in, you assume and you keep going.
You start there, just, and you're gonna find something where all of a sudden it doesn't change.
Yeah, that'd be a no less. It's more of a MATLAB thing, though, right?
Yeah, you can do it, you can write a code to do this really easy. Especially if